So again, we're continuing to try to use the first derivative test to classify our stationary points. Now this one is a cubic function. So now we don't know as much about cubic functions as we do about parabolas, but we can still do the same process. Find your derivative. Set your derivative equal to 0 and solve. This one factors nicely. Once we set it equal to 0, we get x equals 3 and x equals -1. Those will be our critical points. We have no other non-permissible values. So when we go to our number line, those are the values that we're going to put into our number line. We then want to check if I plug something into my derivative in each of those sections, will it be positive or negative? And that will tell us where my original function is increasing or decreasing. So when I try a value less than -1, and I plug that into my derivative, so I picked -2. And personally, I like to use the factored part right here. Because if I plug a -2 into that, I can tell that this, well, 3 is always positive. -2 in here will make this negative, and -2 in here will make this negative. A positive times a negative is going to be positive. So we know our initial function is going to be increasing until we get to -1. Now if I plug a value in between -1 and 3, say 0, well, this is still always positive. This will be negative, but this will be positive. Positive times a positive will always be negative. So I know in that middle section, my function is decreasing. You like I'm using my disappearing pen. Do you like the disappearing pen? It goes away after some time. So in the last section, again, 3 is always positive. And if you plug in something larger than 3, like 5, this will be positive, this will be positive, always positive. So that section's always positive. Oh, you can play all sorts of fun games with the disappearing pen. You can have competitions to see who can write the most of, as much of the alphabet down as possible before the A disappears. It's really stressful, actually. But so now that we've found those points, and we know that if it goes from increasing to decreasing, it has to be a maximum. If it goes from decreasing to increasing, it needs to be a minimum. So it's really nice to have this diagram with the arrows like we have it, because it becomes really obvious what's a maximum, what's a minimum. And then if we want to find out what those actual points are, those points are on our original function. So we plug those values into our original function and find out that at -1, 5, that's our local max. And at 3, -27, that's our local min. So I'd like you to try D. Oh, D has the non-permissible values. Maybe we should do D together. Yeah. So here, our final function has some asymptotes. It has some non-permissible values. Can you see on the bottom that x couldn't be 1 or -1? You could factor the bottom as a difference of squares, and both 1 and -1 are non-permissible values. So when we go and use our derivative, well, in this case, we're going to have to use the quotient rule. quotient rule is what? Keep the bottom the same, derivative of the top. Subtract, keep the top the same, derivative of the bottom, divided by the bottom squared. Simplifying that, we get 6x over x squared minus 2 all squared. So it simplifies quite nicely. And when you set that equal to 0, we have a fraction equal to 0. The only place a fraction can equal 0 is if the numerator is equal to 0. So we're really solving when is 6x equal to 0. And that happens only at x equals 0. Now when we go to put this graph into our, when we go to put this value into our number line to find out where things are increasing and decreasing, we're going to find out that we also have to put in our non-permissible values. So I've got 0 as my critical point. That's the one if I want to find out if it's a maximum or a minimum. But I also have -1 and 1 as non-permissible values. So now I have 4 sections to check to find out if my graph is increasing or decreasing. Again, I would plug things into my simplified form of my derivative. And the interesting thing is on the bottom, because the bottom is squared, does it make sense that that bottom will always be positive, no matter what value you plug in? And when we're checking things, we really only have to check then the top. What happens when I plug a negative number into the top? It's negative. So does it make sense that both of those sections are going to be negative? And when you plug a positive number into that fraction, into the top is positive. So it makes sense that both of those sections are positive. You sort of got used to, in these number line things going up, then down, then up, then down, and switching back and forth. So this one's kind of neat because it keeps the same thing happening. What we're going to find out later is when we go to graph this, we're going to find out there is an asymptote here at -1 and here at 1. And this graph also has an asymptote at y equals 1. You might remember that from last year when you did functions over functions, that if you look at the highest power in this whole thing, it's an x squared. We have 1x squared on the top and 1x squared on the bottom. And if you simplify that, you just get 1, and that's where your horizontal asymptote is. The way that we learn it this year in calculus is we say, what happens when x gets huge? What's the limit of this function as x goes to infinity? And as x gets very, very big, can you see that the subtracting 4 and the subtracting 1 really don't make a difference? It's like you're a billionaire and you lose 4 cents. Will it make a difference? No. If you're a centenaire, which means you only have a few cents, and you lose 4 cents, maybe that would make a big difference. I think I just made up that word. A centenaire. It's like you don't have more than $1. Maybe that. Then if you lose 4 cents, it would make a huge difference. So in this function, we go further and find out we now know that 0 is a minimum. When we plug in 0, we find out that that point is at 0, 4. And this is what we have as information for our graph. I put my asymptotes on there, and I know that 0, 4 is a minimum. How can it be decreasing in both of those sections? Well, this is what this graph looks like. Can you see that that function is decreasing from left to right before -1? and then it's decreasing again here until it gets to that minimum, that local minimum. Then it's increasing and increasing. And so that's what that final graph would look like, and how that sign diagram helps us draw it. But we still had to know some information about asymptotes before we were able to do that. So I'd like you to try the show that part to practice your derivatives. And then we're going to try to find a maximum for this function. Quotient rule. Keep the bottom the same, derivative of the top. Subtract, keep this top the same, derivative of the bottom, over the bottom squared. Simplifying it, we still have an x to the 4 on the bottom. We want an x cubed on the bottom. So there has to be a way to factor an x out of the top to cancel with the bottom. Sure enough, if you do that, everything works out perfectly. If we set our derivative equal to 0, again, a fraction's only equal to 0 when the numerator is equal to 0. So solving for that, we have to solve for something inside of a logarithm. And this reviews grade 12 exponents and logarithms. If you're solving for a variable in a logarithm, your job is to get it as a single logarithm, which here I've got natural log of x equals a half. And once you're at that point, you can change it back into exponential form. The base of natural log of x is e. The 1/2 is the exponent, and what's inside the logarithm is what it would be equal to. So our x coordinate is e to the half. Here's another one to try. Here's our derivative. Now, for this one, because of the way the question is worded, it tells you that there is a maximum between -1 and 3. Can you see that between our two solutions, the only one that's between -1 and 3 is the 2/3? So that one has to be the local max. That being said, we could still do our sign diagram, and we could put 2/3, and here I'll put 6 on there as well. Before 2/3, if you plug that in, you will find out that this section is positive. So it's increasing. Between 2/3 and 6, if you put a value in, you'll find out that is negative. After 6, if I put in 10, can you see that this section is positive and this section is positive? Positive times a positive, this will be increasing again after that. So we would know at 6 we have a local minimum. But the question just said find the x coordinates of this maximum point. Because it's between -1 and 3 and there's only one value, you wouldn't have needed to put that sign diagram to show it. But you're going to find that as we get to the next stages in this unit, which is graphing everything and using our skills in calculus to graph things, we're always going to draw that sign diagram to show where something's increasing, then decreasing. So here we have a function with a variable that we don't know. We know that p is a constant, p is some value, and we want to find the derivative. I'd probably first change the equation to bring that x up as an x to the -1. And then you could take the derivative of each part. and then you get 2x minus p over x squared. There is a minimum value when x equals negative 2. Find the value of p. So what that means is when we plug in negative 2 into our derivative, it has to equal 0. And then the only variable that you have in that equation that you have to solve for is p, a little bit of algebraic manipulation, and we'll find out that p is equal to negative 16. So what we've been doing so far is we have been using calculus to find out where maximums and minimums are. If you're doing a question in your homework using calculus and you're wondering, did I find the right values? Well, you have your graphing calculator, and you can always use your calculator to find maxes and mins. Everybody's aware of how to do this? So you could type in your original function into your calculator, look at the graph, and then find the coordinates of the max or min, and then use those to check, did I do my work right? Is my calculus right? Am I getting the same maximums and the same minimums as what my calculator says?